Okay, looks like I'm just by myself today. Hopefully you guys will be able to see this on the recording okay. All right, I'm hoping that this won't take too long. I just want to complete the second step to that final proposition that we started to prove in the last class. Basically, just to kind of jog your memory in that proposition, the crux of the argument was that if you start in a steady state of a competitive equilibrium in the two-period OLG model where there's no Social Security, if you implement a pay-as-you-go Social Security plan from that point, a very small one that is, that it will unambiguously reduce the steady state capital stock and also lead to a new set of allocations that strictly Pareto dominate the previous ones. It's that latter step that I want to try to show today. And I think in the last part of the class, I even outlined a strategy for how we would try to accomplish this, okay? And that is, what I'd like to do is show that the allocation that an agent would consume over her life in the competitive equilibrium without Social Security lies inside the budget set of an agent at time t facing Social Security payments D. Okay, so that's what I want to do. All right, so the first step here is let me just consider the problem that is faced by a generation that is born in date T in this unfunded pay-as-you-go Social Security system. So if you'll recall, their two-period maximization problem looks like the following. Max over lifetime utility, where you discount second period utility using the discount factor beta, subject to a sequence of budget constraints. The first period budget constraint has your consumption plus your savings plus your Social Security tax bounded by your first period wage. Your second period consumption is simply going to be equal to the gross return to your private savings from the first period plus the return on Social Security, which, as you know, is 1 plus N. Okay, now to make this argument where we show that this competitive consumption bundle lies inside the budget set of an agent at date who is born at date T, who faces Social Security payment D, what I want to do is actually derive this thing called the lifetime budget constraint for this particular agent. It's really simple to do. All you need to do is combine the two sequential budget constraints. I'm going to solve the second period budget constraint for S for savings. That's equal to C2 T plus 1 over 1 plus R T plus 1 minus 1 plus N over 1 plus R T plus 1 times D bar. And then I'm going to use this and substitute it into the first period budget constraint to derive an intertemporal budget constraint or a lifetime budget constraint. So this becomes C1 plus S, which is C2 T plus 1 over 1 plus R, is equal to the real wage plus 1 plus N over 1 plus plus RT plus 1 times D bar. I'm going to swing that over from the left-hand side. And then we can't forget about the Social Security payment in the first period. This is the lifetime budget constraint. And hopefully you can see that it has a nice interpretation. It has the present value of lifetime consumption. So that's current consumption plus the discounted value of second period consumption. 1 over 1 plus R is effectively the price of second period consumption, is equal to the present discounted value of lifetime income, which is your wage, plus your minus the Social Security tax you pay when you're young, plus the discounted return to that Social Security when old. Okay? Essentially, what we want to do here is we want to show that this consumption bundle in the competitive world without Social Security lies inside of this budget set for an agent who is born at date T who faces Social Security. In other words, we want to show that C1 star plus C2 star over 1 plus RT plus 1 is strictly less than WT plus 1 plus N over 1 plus RT plus 1, D bar minus D bar. If we can demonstrate this, then that will, because utility is strictly increasing, agents who are born at date T will want to exhaust their resources and increase consumption up until the point at which the allocations lie on their budget set. So if we can show that it lies inside their budget set, that is the consumption allocation in the absence of Social Security, then we know that agents are going to be strictly better off in all periods with Social Security. So this is the key. This is essentially the inequality that we want to be able to demonstrate that it holds for all T. Okay. So the first thing we should note is that the consumption of the old generation at date T in the competitive equilibrium without Social Security is simply going to be equal to 1 plus R star times S star, right? This is what an old individual would consume in the benchmark economy without Social Security, okay? Now, if at date T we start to implement a Social Security plan, that level of consumption has to be strictly less than what the old generation would consume at date T, which would simply be what it carried over in savings from the previous period, plus that initial old generation instantly gets the Social Security benefits financed by the taxes of the initial young generation at date T. Right? So if we were to, at date T, implement Social Security, pay-as-you-go Social Security for the first time, then the generation that is old in date T would instantly receive higher consumption because they would get the consumption that they would have consumed anyway in the absence of Social Security. Plus, they get the immediate transfer from the current young generation at date T. So C2 star is less than C2T. What about C1 star? Now remember, in a world without Social Security, in the steady state, consumption of the young is just equal to the wage minus private savings, right? That's just the wage minus private savings we know is equal to the capital stock per worker times 1 plus N. That is from the definition of the competitive equilibrium, because K times 1 plus N was equal to private savings. The savings of the young is what determines the aggregate capital stock. Well, what is the wage The wage is the marginal product of labor, which we know is just F of K star minus K star times F prime of K star, and then minus this K star times 1 plus N. Okay, so C1 star is equal to F minus K times F prime minus K times 1 plus N. C2 star is equal to 1 plus R star times S star. Well, that is just equal to 1 plus R star is F prime K star minus delta times S, which is just K star times 1 plus N. So I have expressions for C1 star and C2 star. It's equal to this and this in terms of steady state capital in the world without Social Security. What I want to do is I want to use these expressions to plug them into the left-hand side of this budget constraint. Okay, so C1 star plus C2 star over 1 plus RT plus 1 is going to be equal to, let's see, that is F of K star minus K F prime of K minus K times 1 plus N plus K times 1 plus N times, let's see, 1 plus R star. Let me just temporarily take out this marginal product of capital term for a minute. Divide that by 1 plus RT plus 1. Okay. So the challenge here then is to show that what I have on the right-hand side of this equation, F minus KF prime, that's the real wage, minus K times 1 plus N, that's S, so that's first period consumption, plus, let's see, S, that's K star times 1 plus N times 1 plus R, so that's C2 over 1 plus RT plus 1. The challenge is to show that this expression is indeed less than WT plus 1 plus N over 1 plus RD minus D. That's going to take several steps to accomplish. Okay, so, and it's going to require the use of a couple of tricks in order to express this thing as the appropriate inequality. In particular, what we're going to have to appeal to is the strict concavity of the production function so that I can determine relationships between the slope of the production function, F prime, and the ratio of F to K, which is going to be needed in a few spots. I know that's confusing, but let me try to demonstrate what I'm talking about now. Okay, first, as an aside, the function F is concave. That means that we can actually come up with a restriction on how the slope of the production function is related to F divided by K. Let me illustrate this graphically so that it's easy to understand what I'm talking about. Let's graph the production function, which we know is strictly increasing, strictly concave, and satisfies the Inada conditions. Let's assume that this point here is K star, And this point here will be KT. In this example, we are reducing capital from the competitive steady state without Social Security to some steady state that's lower. So I'm going to have KT be less than K star. All right. The line segment that joins these 2 points here has the following slope. It would be what? F of K star minus F of KT divided by K star minus KT. That's the slope of this line segment that joins these 2 points on the production function. Because the production function is strictly concave, you can see that the slope of that line segment is less than the slope of the production function, the tangent line, at K. It's got to be less than F prime of KT. And that's because the production function is strictly concave. Given that the second derivative is negative, this inequality has to hold. Now, why is that helpful? If we rearrange this, we get F of K star minus F of KT has to be less than F prime of KT times K star minus KT. All of that implies then that F of K star has to be less than F of KT plus F prime of KT times K star minus KT. I'm going to use this inequality that F of K star has to be less than F of KT plus F prime of KT times K star minus KT. I'm going to use that inequality up in this expression that I just did a couple of minutes ago, so that I can start to turn this equation into an inequality and thereby help me prove that lifetime consumption in a competitive model without Social Security lies inside the budget set defined by the right-hand side here. Okay. So how am I going to do that? Again, we have C1 star plus C2 star over 1 plus RT plus 1. On the previous page, we showed that that was equal to F of K star minus K star times F prime of K star minus K star times 1 plus N plus K star 1 plus N times 1 plus R star over 1 plus R T plus 1. I'm just literally copying the same line down I had from the previous page so that it's all on the same paper. Okay. Let's look at this first term here, F of K star. We know that since F is strictly concave, that F of K star has to be less than this term here, F plus F prime times K star minus K. So what I'm going to do is I'm actually going to substitute that term in right here. And by doing that, since I know that this is bigger than f of k star, then that means the left-hand side has to be strictly less than what is going to be on the right-hand side now. So C1 plus C2 over 1 plus R is strictly less than f of kt minus kt f prime of kt, that's minus kt times f prime of kt, plus k star times f prime of kt, that's this k star times f prime of kt, minus the rest of the stuff that's in this line. K star f prime of k star minus k star times 1 plus n plus k star 1 plus n 1 plus r star over 1 plus r t plus 1. Okay, now some of this starts to simplify. What do we know about f minus k times f prime? That is the same as the real wage. So that's WT plus, let's start to group some of these terms here. Plus k star times f prime of kt minus f prime of k star. And then what I want to do is I actually want to group the last terms here that have this k star times 1 plus n on them. And I want to do that by, let's see, factoring out a k star times 1 plus n. And you're left with a 1 plus r star minus a 1 divided by 1 plus rt plus 1. So it's minus a 1 plus rt plus 1, that whole thing over 1 plus rt plus 1. Hopefully you see how I did that there. So what's going to be left? You have a k star times a 1 plus n times the 1 plus r star over 1 plus rt plus 1. And then you have minus k star 1 plus n times 1 plus r over 1 plus r. Those cancel, and you're just left with a minus k star times 1 plus n. So I've combined these last two terms into this composite term now. Okay, let me make another substitution here. We know that KT is decreasing towards this new steady state that I defined in the last class as K bar, where the capital stock is permanently lower and closer to the golden rule. So the capital stock is shrinking. And so that implies then that KT plus 1 is less than KT. Since the production function is concave, that implies that f prime of kt plus 1 has to be bigger than f prime of kt. So what I'm going to do is I'm going to replace this f prime of kt with an f prime of kt plus 1, which is a bigger number, so that the inequality is still going to hold. That doesn't change the sign of the inequality. So you get a C1 star plus C2 star over 1 plus RT plus 1 is less than the real wage plus K star times, now I'm going to sub in the F prime of KT plus 1 minus f prime of k star plus, let's see, some of this cancels, right? You have a 1 plus r star minus a 1 plus rt plus 1. Well, the 1's cancel, and you're left with a k star times a 1 plus n quantity r star minus rt plus 1 over 1 plus rt plus 1. All right, we're getting closer. This is less than WT plus K star times F prime KT plus 1 minus F prime K star plus K star times 1 plus N. Now, R star minus RT plus 1. Well, that's just F prime of K star minus delta minus F prime of KT plus 1 minus a negative delta. So that would be plus delta over 1 plus RT plus 1. The deltas cancel. And what you're left with then is a WT, I'll say K star, times F prime of KT plus 1 minus F prime of K star. Now let me factor out a negative 1 here. This becomes a minus K star times 1 plus N. And then what you're left with inside would be an F prime of KT plus 1 minus an F prime of K star over 1 plus RT plus 1. All right, I've just taken out a minus sign from that row instead of had the plus sign there. The reason why I want to do that is because I see that I've got a common term here. I've got an F prime KT plus 1 minus F prime K star and an F prime KT plus 1 minus F prime K star. I can similarly group those terms together by factoring out, let's see, a K star times F prime KT plus 1 minus F prime K star times quantity 1 minus, what am I left with? A 1 plus N over a 1 plus RT plus 1. Now we're getting somewhere. We know that KT plus 1 is less than K star because the capital stock is shrinking towards the new steady state. And so that implies that F prime of KT plus 1 is bigger than F prime of K star. So this difference right here is a positive number. What else do we know? We're in a dynamically inefficient economy where N exceeds the real return to capital. Therefore, 1 plus N over 1 plus R is bigger than 1, which means that 1 minus a number bigger than 1 is a negative. So we have the present value of lifetime consumption is less than the wage plus a positive number times a negative number. So it's less than the wage plus something that is negative. Well, I can simply take this negative component out of the inequality, and the inequality still has to hold then, right? So this implies that C1 star plus C2 star over 1 plus RT plus 1 has to be less than WT, right? If I just get rid of this negative component here reduces the real wage. So if I just ignore it, the inequality is still going to hold. Well, if this is true, the inequality will still hold if I add something positive to it, right? Well, I can add a 1 plus N over a 1 plus RT plus 1. That's a number bigger than 1 times a D bar. That's positive. And I can subtract a D bar from it. This term here is positive because N is bigger than RT plus 1. We're in a dynamically inefficient world, right? So 1 plus N over 1 plus R times D minus D is a number that's bigger than 0. So I can add that to the wage and this inequality still holds. Well, hopefully you remember that that is exactly equal to the right-hand side of the lifetime budget constraint of an agent who is born at date T who faces an unfunded Social Security system. So what we've shown here through all of these manipulations is that the present value of consumption, lifetime consumption for an agent who doesn't face any Social Security is going to be strictly less than the lifetime income of an agent who does face Social Security. So it's inside of the budget set of agents living in a world with Social Security. Presumably those agents would exhaust their resources to lift consumption over their lifetime and thereby consume a C1 and a C2 that lies on their budget set. So, and this is going to hold for all T. So current young generation, as well as the future young generations, are going to be strictly better off in a world with pay-as-you-go Social Security than agents who are living in a world without Social Security and in which the savings have been overaccumulated to the point at which there is dynamic inefficiency. That is, the population growth rate exceeds the real return to capital. And that completes the second part, or the second step of this proof. Hopefully it made sense. And with that, I will just say that in the next class, we will start talking about the basics of dynamic programming. That really concludes our discussion of the OLG model. Hopefully, going through this proof, you've learned some, or at least been exposed to some tricks on how to do the analysis to prove various aspects of these models. I think that's one of the things that, one of the benefits of going through one of these types of proofs. Okay? All right. No one joined me today. That's okay. So let me go ahead and conclude there, and I will see the rest of you guys next week then.